So yeah, I'm Rob. I'm CTO of a company called Improbable, which is a company based in London, and we're kind of building a new technology for large-scale simulations, specifically simulating things called complex adaptive systems, which is a nerdy word I'll go into at some point. So let's talk about disruption. Everyone's talking about disruption. Sophie, I'm sure, loves disruption. How will something like autonomous vehicles change the world? We know that, it means I'm not going to be sort of driving my car anymore. We know it probably means companies like Uber may change. But there are with these kind of disruptions, there are always these kind of unexpected cascading consequences. Like how are autonomous vehicles really going to affect footfall in urban environments? How is it going to affect parking? How is it going to affect kind of urban design? And when these things are coming along, how do we actually plan for these cascading consequences? How do we plan for these things, these changes? It's really, really hard. And if you look at some academic institutes like the Santa Fe Institute, there's actually an entire world of mathematics called the complexity theory. And the whole premise, kind of boiling down, is you got lots of stuff, and you kind of get how one or two of these things interact. But when you have lots of them, really, really crazy stuff happens. And this kind of example really reflects itself in loads of different areas. One is kind of economics. You have people feel they understand, people as having very simple transactions between each other, we understand quite well. But suddenly when you have tens of millions of people, banks, firms interacting, you get things like flash crashes. And complexity theory is about understanding the kind of how you get this kind of explosion of complexity as you scale up these systems. And this is my favorite kind of toy example of something which really exhibits emergent complexity. It's something called Conway's Game of Life. And it's a very simple kind of simulation where it consists of a little set of cells. And these cells have very basic rules about when they decide to kind of multiply and when they decide to kind of die off. And even with these very simple rules, you suddenly put in 1,000 of them and you get these beautifully complex patterns. And in fact, this kind of environment is so powerful, you can actually use it to simulate absolutely anything, which is absolutely crazy. And this emerging complexity really represents itself in a ton of different areas. So one is large-scale infrastructure. So you have, a city consists of lots of different complex systems. You've got traffic where someone might just slam on the brakes somewhere and then suddenly there's this traffic jam going for miles behind. You've got things like telecommunications infrastructure. Suddenly something like Pokemon Go happens and they're all crapping themselves because telecoms infrastructure isn't built for thousands of people going around with 4G connections streaming down Pokemon. And getting back to economy is so we kind of feel we understand the world of microeconomics, but when you scale things up to macroeconomics is about these beautiful classical equations, just like Newtonian mechanics in the 1800s, about these equilibrium. And when you find these big spikes, people kind of just scurry and kind of hide in a corner in the kind of economic academic space. So how would we normally attack these kinds of problems? People will probably say maybe big data. Maybe we can look at all this data. Data's great, solves all our problems right now, right? The issue is about big data and data analytics when you're looking at disruptive innovations is you're looking at data from now or data from the past. There aren't any cities which have autonomous vehicles we can look at the data of and ask what's going to happen. And this is kind of where a lot of these interesting questions are, is trying to understand these what if questions, these counterfactual questions. What if, by 2030, half of the vehicles in London are self-driving? What are the actual cascading consequences of that? And I guess we've concluded that big data, machine learning, all these tools really can't solve these problems, although they're an integral tool. So the kind of idea we had is, what if you could simulate them? What if you could literally integrate, imagine something like a city, represent every single person in that city, every single vehicle, every single road, building, traffic signal, telecommunications tower, power network, substation, and link them all together and create a simulation of that entire city. Imagine a digital representation of the real world inside of a box. And it's a little virtual laboratory, which you can play around with. You can close down a road. You can replace half the vehicles with self-driving vehicles. You can see potentially the effects of these changes you're going to make. And this is kind of the technology we built called Spatial OS. So the whole idea, this is the technical bit I'll get over and done with. We can look at cool videos. Instead, I guess more recently with cloud computing, people are resorting to using lots of computers. We heard about quantum computation today, and there's kind of this flattening out of the traditional capabilities of a classical computer. We, on our side, are actually looking at using thousands of computers in the cloud to kind of stitch them together to be able to simulate very large environments. But this is very difficult as a kind of like as a person making simulations, because you always have to decide on, let's say I've got 1,000 machines running in the cloud. I have to decide what computation I'm putting on those machines and what data I'm putting onto those machines. And that's a really, really tough thing to do. So what we do is we present a compute abstraction where a person running a simulation thinks about the cloud as a three-dimensional virtual space. And inside this 3D space, I put things into it and define their behavior. So I put into this three-dimensional space cars and define, how cars drive around roads, and I'll probably bring in an academic who understands that vertical. Then I'll put in, all the cell phone towers for the city, and I'll bring in a relevant domain expert who understands how they work. And then the idea is you can stitch it all together and have, sort of a living representation of something. And what this really comes back down to is simulating this kind of emerging complexity of the real world in a virtual world, so you can learn more about kind of our world. So let's look at some cool videos. This is kind of our first real foray into kind of like applied simulation. Improbable has a bit of a background in kind of gaming. And we looked to simulate the city of Cambridge, which is kind of where I studied. And we wanted to simulate every single kind of road, person, and vehicle, and like sort of all the different layers of infrastructure, and just kind of poke it and see what happens. And there are loads of different applications we can talk about, but let's cut to the video. So these aren't like simulations like, someone with an Excel spreadsheet. Like as we zoom in here, we're literally representing every single major layer of physical infrastructure. We're representing every single like vehicle, every single pedestrian inside the city. And we can simulate an entire day of it. So we take things like, transport schedules, which are publicly available. We take the road maps, which are publicly available through OpenStreetMap. And then we speak with academics to kind of understand the dynamics of how like cars drive around on the road, or like sort of, zooming in, you'll see like sort of how pedestrians walk down on the street. So this is like literally the fidelity we're talking about, literally physical pedestrians walking down the road and going to Starbucks. And what we're kind of modeling here is lots of different layers of physical infrastructure, and crucially the interdependencies between them. So if you do something like, a substation goes down within a city, you can see the cascading consequences on other parts of the infrastructure. Things which you kind of maybe might not expect, which is like a really interesting thing to be digging into. So these aren't just like simulations, like the traditional kind of like sort of simulations of late, well, times gone past, where it'd be in a supercomputer, you'd press play, you'd go have a coffee, and you come back and see what the simulation said. These things can be using the power of the cloud so they can run in real time. So I can actually have a simulation of a real city, and I can be like, what happens if this power node went off? And now I can like sort of disable it and see the cascading consequences. It's knocked out the power to the subsequent substations. It's knocked out power to the telecommunications network, the traffic signals, and you can kind of see the emergence of kind of this coming on. So already areas around like the kind of areas of kind of city resilience is a really interesting area here. Think about how to make sort of cities more robust to these kinds of changes happening. You can imagine, like sort of in the US, there's been some really kind of freak weather events happening, seeing like sort of how infrastructure can be like sort of made robust to that as well is pretty exciting. So how did we do it? So, we took pretty much already available data sources from different areas, from, traffic schedules to mapping data to basic census information. And that defines like the kind of the data, the initial starting state of that simulation we want to kind of perform. And then the thing about simulations is you can't just plug data in. You have to kind of define how the things do stuff. You have to define the algorithms for how the car drives along the road, how like buses start and stop, how like sort of trains pull out and do their various things, the algorithms for working out like the cell phone tower kind of like sort of energy dissipation. There's all these different kind of silos of academic expertise you have to unify together. And this is kind of what our tech's very good at doing. So we have a guy who works with us, and his jam, his PhD was simulating waste disposal trucks. We call him Simulation John. He loves that kind of stuff. We bring in people from like the government who are kind of interested in modeling like sort of internet infrastructure. We've been working with telecoms companies to work on the telecommunications infrastructure. And it's like a big sandwich. We're kind of sticking together, adding layers and layers and layers, and working, basically defining the interdependencies between them. And you have this really, really fascinating virtual environment you can use to learn about, urban environments. Because now I can, take this and I can pedestrianize half of it and see what the effects would be on kind of people's commutes. I could, replace half the vehicles with autonomous vehicles and see how things would happen. Or kind of what's happening more recently, we're having spin-out companies use this as the environment for training the next generation of kind of autonomous vehicle fleets, because they don't have any real cities to try it out on yet. They have to have a digital city to see what's going on. And I guess another area which is kind of related but interesting as well is cybersecurity, which is again, a similar problem of kind of emergent complexity. So you've got like a large-scale IT infrastructure. You've got kind of a series of different nodes that interact. But you get this kind of situation where you might have one vulnerability, and that can cascadingly cause unexpected consequences, which, sort of if you piece it all together, you would see, but you don't really have any intuition for. And this is, again, working kind of with another kind of government client to be like sort of creating a way for simulating kind of attacks on physical infrastructure. So you can see here, we define the kind of the starting node which has access to the public internet. You can define the kinds of attacks that are being performed onto it. And you can see how, with that node going down, you can see the emerging kind of complexity of that cascading and like sort of taking out all manner of kind of like sort of different things. Obviously, the visualization looks super cool as well. And then like sort of thinking not just like sort of within like sort of a single company, you can be using these kinds of approaches for understanding like sort of even larger physical infrastructure. So we decided to try and simulate the entire internet, well, specifically the kind of the trunk nodes of how like sort of most data gets routed around. And there's about 60,000 of them. And they have a special kind of protocol called BGP, which defines if I've got some data here and I want to route it to like here, what's the best kind of route to go down and what's the minimum number of hops? So if you have things bad happen, like one of these nodes goes down, these algorithms are always working and they'll kind of reroute the data around the most appropriate route. And this is really interesting to be designing, the internet from a kind of resilience perspective, but the thing about these kinds of simulations is the way these entities interact, these different kind of nodes, is so well understood, you can literally, buy a textbook and it will tell you exactly how they communicate, which means not only is a simulation good for kind of understanding the nature of what this system is like, you can actually use it to actually predict the future. And I guess like sort of one of the things that's being investigated to being used for is an internet tamper sensor. So you have, sort of this is just showing all the like sort of the nodes in the US and how they're connected. But imagine, I guess we've done this for the entire world. And imagine having here this kind of virtual representation of what we think the internet should be doing. And then one day, a lot of kind of institutions have access to telemetry of different like sort of where data is being like sort of routed around the world. We see that something weird is happening. And we can actually use this to create a tamper sensor for the actual full internet. If someone decides that they want to start routing packets through Ukraine for some reason, this system would say, actually, if things are playing by the rules, this wouldn't happen. We can see the kind of the discrepancy, which is very, very exciting. And I guess some closing thoughts on kind of where I kind of see simulation going in the future. You speak to a kind of civil engineer and they're working on building a bridge. And before they build it, we'd assume that they've simulated it, they've run some models, they kind of understand what's going on. You can imagine 100 years ago, there's probably much more of an issue of like kind of bridges falling down because people were kind of eyeballing it. And if you were to ask a civil engineer like about their bridge design and they hadn't have like simulated that bridge, you'd say that they're being reckless. You would think that they're not really doing their job properly. But we do, like sort of the government or like large-scale institutions make sort of similar large projects with kind of no understanding of the cascading consequences of like sort of what they're doing. Something as like Brexit, you have like sort of one simple decision, but there are cascading consequences on a geopolitical scale which we don't understand. So my take with simulation and tools like this is, in the future, this is going to transform the way we do like sort of policy-making decisions. So, I'm going to be making a kind of a modification to the financial system. Well, why do you think that the like sort of like X ratio should be set to blah by the central bank? Well, I spoke to a guy with a beard and he said it was a good idea. Like, we want to go a bit further than that. Imagine having like sort of a kind of a virtual representation of the economy you could use and say, we hypothesize based upon this model that this is what's going to happen. The amount of kind of like public dialogue you could have would be amazing. And similarly with kind of large scale kind of like sort of organizations, like large scale logistics and infrastructure groups, they don't really understand like sort of how to be like planning for the future. All these disruptions are coming, like like sort of drones, self-driving vehicles, but they have no way of kind of asking those kind of factual what-if questions. They have no way of imagining what the future could be like. And this kind of large-scale simulation capability would let them do that, which is super exciting. All right. Thank you very much.
I can see, I'm not sure I can get this all the way over there. So, okay, good. Well done, Lee.
Hi, this is Justin from AT Kearney. I'm really impressed by the
Oh, hey, sorry, I was looking for you. Very
Sorry,
good.
stuck behind here. By the technology, I can't believe the amount of data that must go in. One question for you is, have you done comparisons against events that have actually occurred, and what have the results been like?
Yeah, so I guess like sort of what you're talking about there is almost like validation. So it's a traditional part of when you're performing these simulations. You want to be asking a question about something that hasn't happened before. So a very good way of understanding whether this thing is actually going to say basically not be full of crap is to have it simulate something you do have data for and use that to kind of validate against. So the way we kind of like sort of approach this is the models we integrate into Spatial OS are kind of already best-in-class industrial models. So when we're simulating traffic, we're not just like, eyeballing it. We're working with a company called PTV, which does, traffic simulation. And like sort of they already have an academic department which are verifying that their models make sense. So that's kind of the best way of doing it is kind of working with the different academic institutions to understand how like sort of those different layers make sense in different like industries and understand how it makes sense. And then that's kind of where we piece it all together. But yeah, that's actually a crucial part. I guess another interesting thing we're looking at is you're looking at the big revolution of kind of Internet of Things. Being able to like sort of almost perform the scientific method on a city when it comes to trying to make simulation models is the goal here. Imagine having a digital representation of London not being driven by algorithms, but being driven from data. So like, a GPS in every single Uber driver's car, CCTV, whatever, and you have this digital model. At any point in the future, you can fork it off and you can accelerate it, faster than real time and ask what's going to happen next. But then the great thing is you actually have the real world data stream coming in, and after a few hours you can be like, wait, I was completely wrong, and then you can adapt and you can refine. And like the scientific method is actually a very powerful tool in optimizing a lot of things and learning more about how things work, and now we can do it on a city scale or even a world scale, which is super cool. Good question.
Anyone else? I have okay, there we go, here we go.
Hi, my name is Santiago. I have a question for you around how complex the models can be. Are you able to simulate living organisms, for example, and look at how chemicals or molecules would interact, accelerate trials and things? Yeah,
so that's a really, really interesting question. So I remember speaking to Vijay Pandey, who's a kind of a molecular biologist in Stanford, and he said, a cell is very much like a city. It's a lot of kind of heterogeneous systems interacting. It really comes down to the amount of entities in the simulation which you're kind of really looking at. Right now, we deal with things in the orders of kind of tens to hundreds of millions of entities. Getting to that kind of world depends on what kind of level of fidelity you're simulating it. So if you're simulating kind of the organelles rather than the actual molecules themselves, we might be able to take a crack at it. We've been approached to be used for actually tumor simulation, where like sort of a tumor can be like about hundreds of millions of kind of like sort of cells, each of them again having behavior about how they interact with cells nearby, in the same way a car driving along interacts with cars nearby it. And that's a really interesting angle in terms of like sort of health applications. But we're finding right now, physical infrastructure is a very interesting kind of area for us and very lucrative because it's really hard to experiment with physical infrastructure. With a website, you can A/B test a page and optimize it, but you can't really pick up a building and put it down somewhere else one day and put it down somewhere else the other day and be like, oh, that was actually better. Supply chains as well and kind of like factory floors is another interesting angle.
Very cool.
Great. Well, thank you very much indeed, Rob.
All right.